There's one here. Yeah.
So can I start? Can I ask a question? Oh, yeah. So I have a question for, sorry, how do I?
Hyunseung, yes.
Hyunseung,
Sorry,
yeah.
my parents weren't thinking about immigrating to the United States when they're naming my name.
No. So you mentioned that you need the cheating to be independent of intervention.
Yes.
And that might be slightly, I don't know, it seems slightly problematic for the particular setup you have, but do you think there are other experiments where that might be slightly more plausible? So that's a question for you. And for Anish, you mentioned that you found like modeling conditions under which linear model from one intervention can be transferred to another intervention. And are there like, have you thought about when can the convex combination model, like the synthetic control, can that be transferred across interventions? So those are the two questions.
Thanks for the question. So it's something that we thought deeply about, trying to get rid of that assumption. It's somewhat, I wouldn't say mathematically necessary, but so the designs that we're thinking about are, like how some A/B testing, they would change the pixel by a couple of inches or like change the color by a little bit in some UI related designs. In those cases, and especially in interventions of those type, we think this blinding essentially of treatment, because if the participant is not aware of which arm they're in, then there's no way that the cheater could actually use that leverage that information. So that's where we think is plausible. In the case of our data set, yeah, this is something that we talk about, is that it is possible that, because when they enter the trial, they know what type of thing that they will see. And so it is possible that they might be using that information to maybe cheat in a different way if they saw video, in-person video versus not. But it's hard to understand. Yeah, I need to talk to an education expert about how the cheating mechanism would work.
Just a quick follow-up. So like you said, when the user cannot really differentiate between the interventions, then will there be a different outcome? It's like, I feel like, isn't that a concern too? Like you said, if there are some small pixels that the user cannot perceive, then will there be a difference in the outcome to begin with?
I'd say a very small difference, but a lot of these A/B testing enrolls a lot of participants. So actually, given enough sample size, you'll be actually able to detect if there is any difference. So we think that's so. Some of the citations that we mentioned about Uber trying this and Google trying this, they're essentially doing these kind of things, changing the font size by a little bit, moving the font to the center versus left. And so we think it's in those settings, because we don't even know, we might be in a bucket where they're trying these things. We don't even know if they're on a control arm. And so in those cases, we're blinded. And so even if I'm a cheater, I wouldn't be able to use that information because I don't know what the treatment assignment was.
Yeah, thanks, Russ. So I think the linearity shows up because of, I'm assuming that the target units factor lies in the linear span of the other people. If I now replace that with saying it lies in the convex span, then convexity is the natural thing to do. But if you have a low rank model, then almost by definition, a linear span inclusion must hold. If you don't have a linear, let's say R is actually very large. In that case, may it be the case that a linear model is not sufficient to describe the relationship, but maybe some polynomial of that is. So like one reason to maybe, instead of fitting a linear model, fit some polynomial of the donor group outcomes. The error in variables gets a lot harder when you have polynomials. Yeah, but you can also prove, I think this is the thing you're doing, where if you're saying that the things are being sampled independently from a bounded space, then actually with high probability you'll have other people that are close enough to you. Right? So then even a nearest neighbor style thing, we're not convex, but uniform weights might work. So it kind of depends on what assumptions you're willing to make on exactly that assumption.
It's my turn. So I also have a couple of questions for Hyunseung. I'm sorry if
no, that's perfectly fine.
So one kind of easy one, you talked a lot about data fusion. Would you be able to do data fusion if you had data sets with different epsilons? Yes. And the other question is about the independence assumption. Could you use the Rosenbaum-Muhammad type of sensitivity to do robustness checks to violate?
Yeah. So those are, thank you for those. For the first question about whether we can combine two data sets of different epsilons, yes, it is possible. It just, we have to adjust the R and the R prime and the identification a little differently, but we can adjust them and then we can just kind of, it's effectively weighted averaging between the one estimate from one differential private and the other one from another one. As long as we know that this data set came from that epsilon parameter, and this other data set came from a different epsilon parameter, we can adjust accordingly. The second question about the independence assumption, that, yeah, so this is the direction that we were thinking about before we wrote it up and put it on archive and submit it. We did, I mean, it is something that we're definitely exploring. The thing is, it's hard to have a sensitivity parameter for cheating, and it's not entirely clear. We're kind of brainstorming what will be the right sensitivity parameter that's interpretable, but at the same time also reveal something useful about the null effect or null effect. So this is something I'll be happy to chat with you about if you're more interested, but something that we're kind of brainstorming at the moment.
So I have a follow-up questions also on the definition of cheatings and the assumption. Let's say that you have someone who is reluctant, it doesn't believe that you see the spinner perhaps, and would be, if been told to say something, would not follow that, but if told to say the truth, would be inclined to maybe do that. I don't know, but so is saying truth, would that be that is definitely a cheater, right? Because it doesn't follow. But would that be ruled out under your condition? Because if there's a treatment effect for that unit, right, that would depend on the treatment assignment.
That's a good question. I think so. If the person is acting only on the information about the spinner and how he perceived the spinner, irrespective of and maybe he perceived the spinner differently if he was given treatment versus if he was given control, then yes, then it would affect the assumption, and then the identification becomes quite questionable, and sensitivity analysis may be developed. But if the person is acting on this the spinner information the same way had he or she seen in the control or a treatment setting, then it would not affect our identification result. The key here is that essentially, as long as the cheater starts to act on the treatment information, then it contaminates the response, how the behavior responds, and that essentially has downstream effects on identifying the effects. And so and we can't correct. There's no way to eliminate those group of people if they essentially start to mess around with their outcome based on the treatment side.
And someone who is, do you include honesty in the blue condition? I forgot what you call it. So if I'm reluctant in being told to tell the truth, if I'm reluctant to tell the truth, would I be considered to be a cheater in that setting?
Yes, a cheater we define as to be anyone who deviates in any fashion from the spinner protocol. So if they only deviate if they're on let's in the blue circle but not on the red and the green circle, then they'll still be a cheater because they deviated from the original protocol design.
So I think that in a lot of these settings, there's a worry that people don't understand the design, right? So they don't understand the differential privacy kind of properties of it. So they might not understand that they are private, right? And that would potentially make a lot of people cheaters, right?
Yes, so that's actually, it came up in the IRB discussion, convincing the IRB officer that, what we see yes, it might not actually be yes, and it might be a no. And convincing, yeah, so that it's an effort that we have to take as we designed the experiment to clearly explain this, but yeah, something that we have to do from a more practical angle. Yeah, and so when Minjusha and I designed this trial, we really thought hard about how to explain this, and we had a diagram, we had another explanation, we had all these other things, but there are definitely ways to improve it for sure. Thank you.
So a comment on, you only have one woman teacher. So technically, you only prove that for a woman teacher, because I mean, in-person classroom, students react very differently to women teachers and male teachers, yes. Right? I would believe that it also transfer over to men, but technically, you only have one. And then if you generalize to all lectures, that's. So can you run more experiments?
Yeah, so this is a great point. So we were, the instructors that helped us participate, we were thinking about whether we should include their faces and randomize the type of faces that are being presented, but that would require more effort during COVID. And they weren't, I mean, they were really already helpful enough. So but this is something that we need to think about, generalizability and the different kinds of ways to do the instructor kind of thing. So some current work, we're trying to figure this out and trying to design a more clear way to tease out those effects. Thank you. Yeah, I mean, we actually want to think of computer voices, because that would be more neutral, but yeah, and there's different like variation of a lot of discussion during COVID happened over Zoom actually.
Shall I go? Yeah. I've got a question for Emma. It's about how you incorporate background knowledge in with your CPDAG stuff. So as I understand it, the scenario you outlined for us was one whereby you have some data, you learn a CPDAG from said data using your favorite CPDAG learning algorithm, and then you consult your background knowledge and say, oh, hang on, I've got some background knowledge here, so I can orient some edges, which maybe I wouldn't have been able to orient otherwise. But one thing that occurs to me, when you learn your CPDAG, some of those edges will be oriented. And maybe what could happen is that you then go and consult your background knowledge and say, oh, that's the wrong way around, that orientation. So would it not be better to incorporate the background knowledge in the learning process rather than post hoc?
Great question. Yes. So the short answer is yes, you can do it the other way around. So there are certain implementations of these algorithms that allow you to do that. Not all of them, though. A lot of them only do it kind of post hoc. And I guess there the question would be like, how much do you trust your background knowledge versus data, in kind of what order you would want to do, or like, you know, which maybe you want to drop or not. But yes. So either way is fine with respect to the results, as long as you kind of have an algorithm that does it. So like the tetrad, I think implementation will allow you to add it like pre-learning the CPDAG. I think the PC implementation in PCALG will not let you do some things pre, but not all of the things, but it can be modified to allow it anyway, but it's not there yet. So yeah.
Yeah, so I have two questions. So one for the CPDAG work, the other for the private RCT work. So let me go with the CPDAG first. So you assume that you know the CPDAG, meaning the buckets and the chain graph that connects the buckets, right? So if you run an observational discovery algorithm like GES and stuff, of course, there would be noise. So my question is end to end, although it is technically identifiable, if I finally ask the question, is your final estimator still the lowest variance, taking the whole process into account, is there anything that we can say about it, or have you run some empirical experiments to end to see if the whole thing works? That's my question. So let me also complete the second question for the private. So from what I understand from your theorem statement, you say that you offer protection, differential privacy guarantees for the non-cheaters. Cheaters, anyway, you cannot do anything. So looking at it from a membership attack point of view, because what is differential privacy guarantee, right? The only thing it guarantees against an attack model, the attack model is a membership attack model. So if I knew something about you from some other source, I must not be able to say that you were present in that cohort, right? So that's a rough idea for the motivation. Now, the problem here is if I am a cheater and I want protection for my identity, would that be offered in your RCT is my question.
Okay.
Not that it's desirable, but but suppose if I wanted, I want to cheat, but I don't want anybody else to know. Yeah.
Yeah, sure. I can answer the CPDAG question first. So for us, it's true. We start with kind of assuming we know the graph, and then based on this information, I tell you like what is the best estimator, right? So if you were to learn the graph and you didn't make any mistakes in terms of the causal kind of orientations, missing edges, present edges, then this would still be the best thing to do. And we did some simulations to kind of see how we compare against other methods when you estimate the whole process. And generally, we still do better, though our results are asymptotic, right? So it's like sample versus asymptotic. If you make errors in your learning the graph process, which you probably will make, then that will definitely affect kind of what will be the optimal estimator, because we're starting from this assumption that the graph we have is the correct one, right? Is the correct equivalence class graph. And if it's not, then there could be other things that are better. So I will say that in kind of the process of working with Richard on like this generalizing it to the non-parametric setting, we do kind of see that perhaps some mistakes in the graph do not influence, but it's very particular types of kind of mistakes that do not influence efficiency in the end. Yeah, I guess that's my answer.
For your answer about cheat, that's another great question that we also thought about during the design stage. So what our theorem suggests is that you shouldn't cheat, because if they cheat, then because we don't make any, for the differential private theorem, we don't make any assumptions about the cheater, how they respond to treatment. So if they're clever cheaters, but they actually just report what the opposite of the response, then technically you can attack it and then actually discover it if you consistently know this pattern. So what our theorem suggests is that maybe you should be honest when it comes to these things. But we also have to work on this, communicating this, that it is differentially private, what differential privacy means. And actually we spent quite a bit of time when you design this trial to actually try to convince this idea, but we're not entirely sure if it's successful, but it's something that we need to definitely work on in that area.
Do you tell them that, privacy guarantees exist only for non-cheaters and non-cheaters? Just from
no, for this trial we did not. We did not. For this trial we did not. But going on ongoing trial we'll design. We'll probably incorporate this. Actually, we spent a lot more time convincing the IRB officer to release the individual level data, and based on that experience, we think we need a better way to do this. Actually.
So I have a question for Hyunseung. I have two, so maybe I can ask the first one and ask the second one after. That's a good order. So I guess one of the things I was thinking about is, if you do covariate adjustment, then if I want to replicate your results, I need to have the covariates in my hand, and the covariates themselves could be private. You might want to be privatize them. So maybe you have to add some Laplacian noise or do whatever kinds of mechanisms one wants to do. On the other hand, like if we want designs that try to have some covariate balance or depend on the covariates in some way, if I want to replicate your results, if I want to like do a variance estimation, let's say I have to know certain types of inclusion probabilities or correlations between treatment assignments. And if the design depends on the covariates, I can learn the covariates, or I can learn at least, I think I can learn enough to break different. I think differential privacy may not hold. I don't know what attacks I can do. But so I guess like, how do you think about if once covariates, okay, well, I guess my question is, in order to replicate results, I need to know covariates and I need to know the design, but these two are related. And if the covariates are private, how does this all play together? Have you guys, I'm sure you've thought about this. What are your thoughts on this?
Yeah, so another fantastic question on the practical aspect, and it also has implication in method and theory too. So when we designed our covariates and asked them for responses, they could respond in any way they wanted to. So they could lie, cheat, fake, because the thing at the end of the day is when we proved our covariate adjusted estimator, the model doesn't matter and it will still be consistent. And so obviously if they provide more honest things, and if you can model the privatized response in relation to the covariate that they provided, then we get more efficiency out of it. But that doesn't mean that they don't have to provide us with complete honesty about everything that we asked about the thing. And the second thing is actually the design of the questions themselves. And so we went back and forth with the IRB about what kind of questions could be asked, and then even though they could not even, they don't have to answer to it, and as well. And so, and I think that's a more of a subject specific or the question specific thing. So we were able to ask questions about like how many courses that they take in about algebra or computer science courses and all these other things. But I think, yeah, there's some questions that we weren't able to ask just because of constraints on our end. Yeah, but I think there's a trade-off here because some covariates are highly more predictive of whether you're going to pay attention in lecture or not than other covariates.
Sure. Thank you for your response. My second question, I have more follow-up on that. We can talk after that. My second question is, as I've been learning more about randomized control trials and when people do them and all the different, ways and places these are done, sometimes I ask myself, like, why do we do this? Why do we want a randomized control trial? Like, what knowledge did we gain? And here it's usually statistical knowledge that we didn't have beforehand from some other kind of means. I guess my question is, in the way that you're allowed to reveal this information. Like, you know, there's all these studies you put up that said like, it's better to see the instructor's face. And like using my own intuitive knowledge, I just know that to be true. And you're like, oh, we can't replicate these studies here. So we're going to like do a control trial on our students, but you could just like ask them. You could just ask like, do you like this or that? And I don't know what incentive they have to lie about that. So why did the department do this? Like, why is this a good idea? What are they doing? Why? Yeah, that's my question is, why did they do this experiment? And what were they hoping to gain that they didn't already know? Or why did they not go with the alternatives?
So I have to be careful here because I'm currently in a, I'm in the promotional stages of my career. So, but no, I mean, just to be clear, the department didn't force us to do it, and it was just a question that was among COVID all of us who were doing instruction about having camera on, camera off, because some of the students in Wisconsin, they're actually doing it remotely. And so they can't even come to campus. And some parts of rural Wisconsin don't have internet connection. And so there was a bandwidth issues and fairness issues that came up. And then there was this general discussion among the instruction committee and TA committee about, you know, what is the best way to still deliver quality education while, you know, and what will be the effect of this and how do we do this? So yeah, so that's the general question. And then we just framed it, we just provided a design that, and also my frustration with just clinical trial, getting individual clinical trial data kind of coincided. And so we provided a way to study those type of questions. But yeah, by no means the department didn't force us to do it, nor the department would be fine if he didn't do it actually.
But if I may ask one, why not just ask the students? Do you like video on? Do you like video off? That's so much easier than running a control trial. Why did that not happen?
Yeah, so we did also have those questions, not even at the department level, but at the entire school level. And so, actually, I don't even know the individual level results of that. It's only summary statistics are revealed. So actually, there might even be better opportunities to apply, maybe not even RCT sense, but just local differential privacy really to those survey results and actually get, so that we can actually pull that observational data into actually having a better estimate for some of our model of things that we built. But yeah, I mean, the school itself, I'm sure other schools did this too, actually asked this question during COVID semester, online COVID semester. Yeah. And so, but we just went a little bit further and we just wanted to also see whether we can actually do this. And also, I wanted my student to actually learn how to collect good data, because good data means that it's easier for method interpretation. And not many students, and myself included, learn how to collect good data. We just know how to analyze data well, actually.
So first of all, I want to thank all the speakers for 3 great talks. So my question is for Emma. I guess at a couple of places in your talk, you sort of hinted at causal inference as being this 2-stage process where we first have to learn some kind of underlying structure and then we do estimation of effects. And as you said, this machinery for sort of rigorous causal estimation that you presented is valid, assuming that we are given this correct DAG in the first place, or CP DAG. And so I guess my question is, it's related to a couple of questions that we've already heard, but I'm wondering if there is still some notion of statistical validity, even if we have a misspecified graph. Like, of course, there are different kinds of graphs that will give us the same kind of causal effect for, you know, a given causal question. But maybe some other causal graphs are still useful despite being incorrect. So I'm just wondering if there is still something that we can say like, hey, you know, I'm computing this causal effect, but it still has some form of statistical validity in the context of this graph. For example, I'm projecting the true causal effect somehow in some appropriate sense onto this, you know, toy approximation that I've come up with. And I think that like, there are a couple of reasons why that's important. Like one reason is definitely when, you know, we're estimating these CP DAGs from finite data, but of course, even if we have domain knowledge, you know, there's no guarantee that that domain knowledge will actually spit out the correct graph. So I guess this is kind of a philosophical question, but I'm just wondering, is there still a way to think about statistical validity if we're in this misspecified setting?
Yeah, thanks. This is a complex question. So, okay, there's a few answers here. So I guess in some sense, right, so learning the graph is tough, and generally things that we have don't perform perfectly and also don't perform well a lot of the time. So what I would say to that is few things. So one is, I guess you can see or I can think of an MP DAG or like this MP DAG as like, you started with a DAG and you've removed some information, right? So you can say like, I guess, so in that sense, like the effect is identifiable regardless of what orientations you have, like on these undirected edges. So in a sense, you're kind of, I guess, to those mistakes, you don't care about those mistakes. In terms of adding edges versus removing edges, we don't have in this work results on that. That has somewhat come up a little bit in the newer work with Richard, but it's by no means complete. So we can say like, oh, if you have this edge present in addition to all the other edges, like nothing will be affected, the efficiency, the consistency, and so on. Yeah, so, but a lot more work is needed in that sense. I also know that there's like a lot of, people look at also like the G formula and stuff, and there's this other commentary on like, well, the G formula really requires a lot of your graph to be correct, right? Whereas maybe some adjustment or some IDA would just need like the parents of certain nodes to be correct. Like you don't care about the rest of the graph. So there are certain like arguments of that. What we've seen in practice, like even if you estimate the graphs, this G formula approach does tend to do better than these parent approaches. So it seems that like there is some, I don't know, that this still somehow is helpful, but yeah, I don't have a precise quantification. In terms of kind of the whole two-step thing and why do we do this in two-step where we first learn the graph and why don't we just kind of directly learn some things? There's very little work on that. There's some really nice papers on this, like this Entner, Hoyer, Spurty's paper that makes certain assumptions and then they're able to do that directly. There's some of Sophia's work that I think is great, where she uses the graph more like a tool, but then just works purely with data and has no kind of a need to learn the graph directly. But yeah, it's definitely an open problem, and I don't know like how much of the graph can you kind of flub and still get the correct answer. Yeah.
I have two questions for Anish. I will do Chris's procedure and ask one after the other. So the first one, the first, yeah. So the first one is slightly more kind of less conceptual, and the second one is conceptual. So I don't remember what you called it, but basically that you can learn the structure for the potential outcomes that you don't, the intervention potential outcomes from the control potential outcome in the pre-intervention period, that you can kind of the same structure. I don't remember what you call that assumption, but I was thinking, could you do a type of placebo test to test that assumption where you try to replicate a unit that is a certain treatment that you do observe, and then you compare those to time series, the artificial synthetic time series with the observed one?
So just let me see if I understood the question. So you're asking, if you hold out the data of a patient that got therapy 1 and how well you could recreate it? Absolutely, that's the first thing we always do in all of these settings. And you can see that the mean squared error is, or like the R square is relatively good. And that's the first thing we do in all of these settings, is to ask how well could we recreate it for a given therapy. If we held out, 90% of the patients, could we still recreate them? And a related answer to that question is that how many patients do you need to be able to recreate everyone, right? So like, why do we pick 50, for example? In general, we found that if the number of patients you have is approximately scaling is like R square or R cubed, where R is your estimated rank, that seems to be kind of the golden point where it starts getting very accurate in this cross-validation sense. So that's kind of like the heuristic we generally apply.
Okay, so the reason, so you try to recreate the expected time series, right? You have this error term, but when you do the comparison, that would be you would have that the error of the realized expectation, right?
Yeah.
So I guess you can only measure this when you're averaging between different units, but your targets, right, are individual treatment effects. So the validation exercise would be with respect to an average.
Yeah, so there are two ways of doing it. One is you average over people for a given time step, for example, or for a given person, you average over the entire post-intervention.
Okay.
So both.
Okay,
yeah. Exactly, to get rid of the noise, yeah.
So my worry in that case, right, is that you would have some type of, you would be, let's drop it. The second question is conceptual, and let's return to my questions during the talk, and sorry for interrupting you, but to me, a randomized controlled trial is something extremely precious, and because it requires very few assumptions. And then with while I really like, and especially the matrix completion view of centric control, I really like it, very sympathetic. They're considered stronger assumptions, right? Compared to like vanilla RCTs. And if we can estimate the marginal distributions of all the potential outcomes without making those assumptions, what does this, like the tensor completion approach bias if we have RCT?
Well, if you don't do any fancy stats on top of the RCT, then what you're estimating is, for example, the average, you compute the distribution of the people who got therapy 1 minus the distribution of people who got therapy, the placebo, and you look at that difference, right? But that would hide, for example, if there's some subpopulation that it worked really well on, right? And so that's what we're trying to do, is that this is exactly the problem, is that the average treatment effect here was negligible. And we were trying to still salvage this, as you call it, precious clinical trial, that and see if we could find a subpopulation that it works on. So if the average treatment effect is enough to make a decision, then there's no reason to do any of this. But in many settings, it's not, right? I mean, with like COVID, what's happening, we run a clinical trial for people above 65, and we run a clinical trial for people between 5 to 15, and so on and so forth. And it's not even clear that age is the right way to be, right way of creating subpopulations. And so the hope is that maybe this way can help you impute outcomes for people you haven't tried it on. And maybe it just functions as a recommendation system of which trials to run, because it's so expensive. And maybe that's kind of the way I think will be the most useful, at least in the coming years, is more just a recommendation system of which subpopulations to try which therapies on.
Yeah, that makes sense. Thanks.
Okay, so thanks again to the 3 wonderful talks in this last session. Let's give them another applause. And thank you to all the speakers, I think, for really, really wonderful talks, like to this very broad audience, of taking this into account and just giving very accessible talks for everyone. I think it has been really, really fun. I'll turn it over.
Yeah, I just want to add to that. Also, thanks to all the great audience that's why we planned this panel session, to have more people have a dialogue instead of just the speakers. Many of you could have given talk too, but we couldn't have everyone. So this is great. Everybody had the chance to really engage and take advantage of the panel. So I really enjoyed it. I'm kind of like a little outsider, but it's great.
Great, that's great for us. So thank you to everyone. And I think there is one more announcement for how we're going to continue this week.
Yes, tomorrow we have application. Vasilis will give a talk on challenges and opportunities of application of causal methods in industry settings. We're going to meet at 10 a.m. and the talk will be available on Zoom as well.
Where?
116, I guess. Thank you.
That's great.
Yeah. Thank you very much.
Maybe you should give applause to all the staff support.
Yeah.
For those of you who are traveling home, have a safe trip. I hope to see you in the not so distant future in person.
Again, yes. Great. Thank you, everyone.
Thank you.
Lots of minutes.